Thank you all for attending this session. We hope our idea stimulates interest, curiosity, argument, and other questions to transition to a cleaner energy future. Our idea is a mere hypothesis based on an integrated assembly of well-reasoned assumptions. Since creating the paper behind this presentation, we have seen our assumptions pass and fail validation. This presentation is exemplary of the dynamic and changing nature of energy transition. What is certain is that we are working to an aggressive timetable that demands immediate action. In the worldwide commitment to cleaner energy, gas turbine mines are challenged to make the gas turbine cleaner. We've met similar challenges in gas turbine history with the advent of single-digit NOx combustors. This presentation is evidence that we are meeting that challenge again with combustors that will add low carbon to low NOx capabilities. That will maintain the gas turbine as the cleanest publicly accepted power generation method having an on and off switch. We are working in degrees of possibility and probability. We are not alone. Our colleagues in other power sectors are working on their own promising technologies. Factory fabricated nuclear reactors, advances in safe fission, the hope of fusion, large vanadium flow grid size batteries, and the development continues. We wish them success as there is no clear single solution. Our job is to make the gas turbine serve in many ways. This presentation suggests one of the quickest ways to impact the rapid growth of clean, reliable power. We are challenged to quantify the sensitivity of our proposed solutions to technological, economic, socio-political, and concern for environment influences. We recognize the delicate balance between clean, abundant power and affordability for everyone. The paper behind this presentation was written before the full impact of the war in Ukraine and the emergence of AI like ChatGPT on the world. These events highlight the difficulty in envisioning the energy and power ecosystem of 2050 or even 2030. There is no silver bullet. Society will need an arsenal to defend our robust and affordable power consumption lifestyle while securing the world's climatic future. In this presentation, renewables will refer to solar and wind. Solar and wind provide us with abundant cheap power and too often unwanted power. The intermittency of both solar and wind impedes its usefulness, value, and growth. How is this problem being solved today? In the US, we could serve at least 60% of our total annual power demand by building more renewable capacity. Renewables are supply-driven resources, and our consumption is demand-driven. The resulting mismatch creates excursions in the value of power. Historically, our power resources were dispatchable. Renewables do not allow us that control. Our most rapidly dispatched traditional large-scale power source is the gas turbine. Advanced class gas turbines are the most efficient producers of power from hydrocarbons. Combined with vintage design legacy turbines, advanced class gas turbines support an increasingly more volatile grid created by renewables. Their advantage over thermal power plants is their relatively fast start and ability to get to rated output quickly. The natural gas-fired turbine has become the dependable, large-scale, rapid dispatch backup for solar and wind power. Both old legacy and newer advanced class gas turbine assets have been increasingly asked to respond to volatile conditions created by an increasing contribution of solar and wind power. This mode of operation is costly to the owner-operator of gas turbines and stresses the business model upon which many gas turbine plants were built. This is especially impactful to advanced class gas turbines in combined cycle configuration and some without diverters to enable fast cyclical startup and operation. Turndown, fast start and loading, and temperature improvements have become imperative for most existing gas turbines. The financial impact of this unprecedented operation on gas turbine owners depends on where it is on its payback timeline and if it was built for simple or combined cycle operation. Most gas turbine owners are utilities, and in North America, those utilities pass cost increases to their customers. If the cost increase is attributable to the increased use of solar and wind power, then we define that increase as the green premium paid to use solar and wind. It is the price we are willing to pay for cleaner power. It's no surprise that gas turbines are dispatched in simple cycle mode with growing frequency. Availability is increasingly valued over the efficiency of combined cycle gas turbine operation. The duck curve, or valley of death, is an enigma. Solar and wind provide the promised cheap power, but the value to the grid makes developing more solar and wind capacity unattractive. The challenge is to balance this abundant power through long duration energy storage, known as LDES, to create long duration grid support, LDGS. Solar and wind developers must integrate LDGS capability in their contracts. The gas turbine industry recognizes its unextractable value to the power grid. Our ability to use hydrogen in our gas turbines pushes us for even greener electricity today. Today, vintage or legacy gas turbines can fire on hydrogen or blends of natural gas and hydrogen up to 100%. Legacy and legacy design gas turbines can fire on 100% hydrogen today. 100% hydrogen firing advanced class turbines are in development, but OEMs now offer 100% hydrogen capable legacy design turbines. Aftermarket providers make it possible to modify legacy gas turbines by replacing vintage combustors with hydrogen and hydrogen blend combustors. Here is GE's publication of its capability to fire on 100% hydrogen on its legacy class gas turbines. Hydrogen-fired gas turbines are carbon-free. With the advent of combustion technologies like micro-multi-cluster combustors, gas turbines can burn blends of natural gas and hydrogen up to 100% hydrogen. The hub approach is essential to the utility of hydrogen. Hydrogen is not easily moved without a lot of work. Liquefaction is the most economical way to move significant amounts of hydrogen energy by truck, train, or ship. Losses from boil-off can be as much as 80% per shipment. Made-for hydrogen pipelines will be most suitable for hydrogen transmission in liquid and gas forms and reserved for the most valuable end users, like long-haul trucking on major interstate highways. Moving hydrogen through pipelines takes 3 to 5 times more work than natural gas. In this example of proposed U.S. hydrogen hubs, we see most are located on oil and gas basins, except the Pacific Northwest, which has abundant hydropower. To understand these hubs, we must look at the sources of hydrogen. The most anticipated source of hydrogen is by electrolysis of fresh or seawater using waste or curtailed energy from solar and wind power. Hydrogen is stored locally for use by nearby industries and power producers. Remember, hydrogen is not easily moved. Hubs created with hydrogen produced from this surplus solar and wind power and used locally are called green hubs. Electrolyzers will make hydrogen from fresh and, with development, salt water in a pure green hub scheme. Price should improve with cheaper materials and improved manufacturing. Large-scale electrolysis favors alkaline systems running at relatively higher temperatures than PEMs. Most green hub schemes call for fuel cells to convert hydrogen to power. Fuel cells will be most impactful in distributed power, transportation, shipping, and small-scale hubs. As most fuel cell manufacturers also make electrolyzers, the division of resources will retard the production growth of one or both products. Even in green hubs, legacy design gas turbines will do the job of large-scale power production. Legacy design gas turbines are relatively inexpensive and currently more ready for conversion to fire high levels of hydrogen than advanced class turbines. Molten salt storage is a promising technology for enhancing the efficiency of existing gas turbines and storing excess solar and wind energy. By storing heat energy, molten salt can help to balance supply and demand, thereby arbitraging clean, cheap solar and wind power. Fundamental to the rapid scaling of hydrogen use in support of solar and wind is creating hubs where solar and wind are co-found with oil and gas. Hydrogen, made from hydrocarbon in all cases, must utilize or sequester the resulting carbon. Blue hydrogen hubs are best located in existing oil and gas fields where the feedstock is near and carbon can be used for further mining or sequestered in nearby spent wells. Most patches offer land for deep and lined concrete vessels to store hydrogen at low pressure and high volumes. The benefit that hydrogen from hydrocarbons offer is large-scale production and the economy of scale of that production. Gas turbines need that scale of production support from solar and wind, and greater consumption scale results from large offtake when industries co-locate near the hub. Co-located industries will drive the price of hydrogen, enticing reforming companies to establish large-scale production. Electrolyzers will become cheaper and more available, enjoying converting and using curtailed or excess power from renewables. This is an optimum configuration, using the abundant cheap power from renewables when available, and electrolyzers when they can be made cheaply and in large quantities. Co-locators will further drive large-scale production of hydrogen, which will drive down the price of hydrogen. Here, we add fuel cells to create a full case configuration for the hybrid of blue and green hubs. A max case would include molten salt storage, allowing for the highest efficiencies and flexibility for power arbitration. Unless used for a very valuable application, hydrogen should be stored where it is made. It takes costly work to move hydrogen. The higher the pressure at which hydrogen is stored, the greater the work and the more difficult it is to contain. Technology and construction methods used to build large volume lined concrete tanks are mature and, along with natural caverns, have contained our nation's strategic gas reserves for decades. There are many companies experiencing this work. Blue and green hydrogen hubs will use similar large volume storage. New storage methods may further improve CapEx for large-scale storage projects. This is the view of gas turbine power and energy supply in the US today. Most turbines are not co-located with oil and gas reserves. This is our aggressive view of the growth of wind and solar when contracting with the value of uninterrupted power through the support of co-located gas turbine power. The alignment of four conditions is necessary to create valuable clean power to support growing solar and wind generation. A grid that values uninterruptible, cheap, clean power, cheap fuel and gas turbines, clean hydrogen at less than $1.25 per kilogram, like that produced from hydrocarbons and legacy gas turbines. Available technology for retrofitting turbines to burn hydrogen up to 100%. A location with socio-political support, feedstock for making clean hydrogen, use or storage capacity for carbon, transmission lines, wind and/or solar, and industry off-takers. Today, these precise conditions exist throughout North America, from Kern County, California, to the Midwest. We project hydrogen prices that will approach $1 or less. This is sensitive to many factors. It will be heavily influenced by co-located industry. Here are our projections for the relocation of existing gas turbines. This does not include the deployment of newly manufactured gas turbines. This typical week in the US generation illustrates the effects of solar and wind on serving the traditional demand and supply curve. Here, we have illustrated batteries and hydrogen power added to the grid mix. As gas turbines will provide large-scale generation in the near future, we project they will make up at least 70% of hydrogen-fueled power. A pivot tool we made for this chart allows for testing various values for sources. This tool is available via QR code at the end of this presentation. This chart illustrates the inequity in the value of dispatchable power to the grid. Renewable supply, together with the demand, drives the value of power. When the power source is predominantly solar on a good solar day, for example, and demand is low in its daily or seasonal cycle, its value is low. However, the uncontrollable loss of solar makes the gas turbine and the hydrogen that fuels it valuable in providing sustained clean power. We have several paths to making hydrogen from hydrocarbons, all at various stages of maturity and proven efficacy. Development of in situ processing using air, CO2, and oxygen with optional heat and water is at an early level of readiness, but has demonstrated effectiveness at its pilot plant in Saskatchewan. This method promises hydrogen at sub-dollar prices. In a version of in situ hydrogen production, a recent microwave technology method is being repurposed to hydrocarbon production. Cheap electricity from renewables at an estimated 2.5 cents will provide hydrogen from pyrolysis and in situ reformations of hydrocarbons at less than $1. Other reformation processes will yield hydrogen at less than $2. Electrolysis will generate hydrogen at under $3. The price of pyrolysis used in this comparison was quoted based on the value of carbon black, a useful byproduct of the pyrolysis process. If pyrolysis becomes the ubiquitous leader in low-price hydrogen from hydrocarbons, then the value of carbon black will likely decrease. A very important feature of pyrolysis is that it utilizes carbon and eliminates the need for underground sequestration. This means hubs outside of oil and gas patches can make clean hydrogen from natural gas where available. Like all hydrogen production methods from hydrocarbons, other than traditional steam reformation with carbon capture, pyrolysis is in its early readiness. Implementing the methods presented in this proposal will necessitate advanced financial modeling. It is important to consider the impact of intermittency on hydrogen production costs, which is often overlooked. The various processes outlined in this presentation, including electrolysis and hydrocarbon reformation on a large scale, are negatively impacted by power disruptions. Consequently, more expensive non-renewable electricity must be considered when estimating the cost of producing hydrogen. We can now enable solar and wind power to have a larger role in providing clean, cheap, useful power to the grid. Gas turbines are solving the intermittency problem and are growingly being dispatched for fast start and loading, including combined cycle gas turbines whose original value was efficiency. With the successful application of dry, low-emission combustion, natural gas-fired gas turbines have been the cleanest large-scale power source after nuclear power. New combustor designs and legacy gas turbines now allow us cleaner emissions by enabling the use of hydrogen in blends with natural gas up to 100%. Hubs made of wind, solar, oil and gas fields, and industrial off-takers will produce large-scale hydrogen for sub $1 per kilogram. Electrolyzer manufacturers can allocate their limited production output to hubs outside regions of oil and gas. Hubs will be essential to the success of hydrogen, as the work to move it will make it useful only in the most valuable applications. Hubs aggregating wind, solar generators, oil and gas fields, and industrial off-takers will result in large-scale hydrogen production necessary for sub $1 per kilogram. Electrolyzer manufacturers will prioritize customers by allocating their limited production to hubs without access to hydrocarbons. Hubs will be essential to the success of hydrogen, as the work to move it will make it useful only in the most valuable applications. With this in mind, hydrogen-fired gas turbines will be moved to hubs and retrofitted to fire on hydrogen. As we call it in our brainstorming sessions, a FEMA switch may be the most critical value proposition for the wind and solar supporting clean combustion turbine. It is triggered by an extraordinary event caused by nature or man. In a strict clean power contract where the gas turbines are expected to fire on 100% hydrogen, the operator might be penalized for using natural gas. Most contracts will recognize this critical circumstance, possibly life or death in nature, and allow natural gas operation. If contracts permit, there could be windfall revenue due to the extraordinary value of power during these times. One windfall event could accelerate these projects' payback and fiscal attraction. Many solutions will measure the success of the transition to cleaner energy. Clean gas turbines enabling solar and wind power are part of a complex picture in which many engineers, scientists, entrepreneurs, leaders, politicians, policymakers, and people will determine the solutions we adopt. Thank you for your engagement this afternoon. We hope our presentation inspires the talented people working on gas turbine technology and all the essential supporting technologies to a deeper commitment to our solution. We encourage discussion and productive argument. The authors welcome your communication. Thanks again. The QR codes you see in this presentation will take you to a downloadable copy of this presentation, data summarized in this presentation, and a tool that enables you to change the power mix on a typical demand week. All documents linked to the QR codes are in revision and temporarily disabled.